we have discussed two scenarios, mutex, semaphores, mutex and semaphores. Now, with mutex and semaphore, there is one thing which is common. The thing is, whenever it is not available, that means either mutex or semaphore. If it is not available, and you are, let's say you are performing a down operation, or you are performing a mutex lock operation. When you are doing a mutex lock and you are performing a down operation, whenever this particular resource is not available, what will happen? Your process will be put to sleep. Your process will be blocked. So this is the thing which happens. Now this is perfectly fine as long as you are dealing with a context which can sleep. Okay, for example, the process context, the thread context, and all those kind of things. This particular thing is perfectly fine in those scenarios. But there are certain scenarios where you are not allowed to sleep. For instance, interrupt. Interrupts context is where you cannot sleep. Sleeping is not allowed in the interrupts. Okay. So then now the question comes is, let's say I have one resource which is being shared between the ISRs. Quite possible, right? Let's say, for example, I have the E square prom. Okay, and to the E square prom, there are two interrupt contexts which are writing. So there is one ISR1 corresponding to one guy and one driver, and there is ISR2 corresponding to the other thing. So now, if they access the E square prom directly, okay, that means like both of the guys are concurrently accessing it, then it will get corrupted, right? If I basically try to access this from the ISR concurrently. Or let's say there is a global variable ABC. To make it simple, there is a global variable ABC. This ABC variable basically is being touched here, ABC plus plus, and here you do ABC minus minus. Now, if I don't protect this variable, if I don't protect this variable, there are chances that it will get corrupted, right? Concurrency issues may happen. So how do I protect? So one of the way to protect, as you know, is you can do mutex lock. But mutex lock, what it will try to do? It will basically try to put this particular guy to sleep, which is not allowed. So what shall we use over here? I can't use the mutex related stuff. I can't use the semaphore related stuff. Then what should I use? So this is where we have something called spin.
Spinlocks.
Okay, yeah, right. And this is where we have the spin lock. So let's see how does the spin lock work. So everybody, the problem statement is clear.
Yes, sir.
Okay, great. So in the interrupt context, when you are dealing with, you will be typically using the spin lock. Now let's understand how does the spin lock operates. Okay, so now spin lock. Let's say first of all I'm taking up the case of the uniprocessor environment. That means I'm taking a case of uniprocessor environment. That means I have only one processor. Okay, like BeagleBone Black. BeagleBone Black just has a one processor as such. And to start with, I'm taking the scenarios of two threads. Okay, let's say I have two threads or two processes, whatever. I would call them as a task, for instance. I will take the scenario of task 1, task 2 over here. And what I have is this task 1 is having a priority of P1, which is less than task 2 holding a priority of P2. That means my task 2 is of higher priority. And this is the uniprocessor, only one processor I have got over here. Okay, now what happens is let's say we are using over here spin lock, spin, unlock, and here also we'll be using a spin lock. So if you see from the operation perspective, spin lock is very much similar to the mutex in the sense you have two operations. You basically have lock, unlock, lock, unlock. So, as usual, when the lock is available, you will get into the critical section and you will go about doing the stuff. But where does it differ from the mutex is if the lock is not available. Let's say you basically try to acquire the lock, let's say in thread 2. If the lock is not available, your thread T2 will not sleep. It will not be able to sleep. It will not be put to sleep. Instead, what it will be doing is it will do the busy wait. It will do the busy wait. And this busy wait part of it, that means continuously checking for the lock to be available. We basically call it as spinning. Spinning. So you can say I'm kind of doing the things. Of course, in an optimized manner, it would be implemented. It's not like it will be doing a tight loop, but I'm just giving you the kind of like a high level view. What I mean, while lock not available, for instance, while lock not available, do busy wait. Kind of. While lock not available, do the busy wait. Of course, it will be done in an optimized way. Okay, spinning will not be like a tight loop or something. So while not available, I'll do the busy wait. So that is where spin lock differs from the mutex. If the mutex lock is not available, you are basically going to be put to sleep. But if you use a spin lock, you're not going to get into the sleep. Instead, what you are going to do is you are going to spin. That means you will be waiting for the lock to be acquired. Okay, so this is a busy waiting, and over there it's a yielding. And when you use the mutex, what you do is you basically yield the processor. Yield means taken off. That means you will be going into some wait queue related stuff. But here you will continuously remain in a run queue. This is where both of the guys are differing. Hope it is making sense. Now, let us now see what problems we might run into when you do this stuff. Okay, so let me take another page. Over here, we discussed about the thing like I have a T1 which has the priority P1, which is lesser than T2, which has got the priority P2. Okay, the priority of P1 is lesser than P2. Now I basically do the lock, I do unlock over here, I will do lock, and I will be doing unlock over here. This is spin lock, remember, this is spin lock. Both of these are spin lock. Okay, so let's now understand. And this is the uniprocessor environment. Only one processor we have got. Okay, so uniprocessor environment. Now let's understand what problems what challenges we might face. So let's say T1 acquired the lock. T1 acquired the lock, and while it was over here, it was in the middle of performing that operation. And in the meantime, it happened so that T2 became runnable. Now T2 has got the priority which is higher than T1. Okay, T2 has got the higher priority which is higher than T1. So that means as soon as T2 becomes runnable, the scheduler will give this guy the preference because it's of higher priority. It's a real-time scheduling we are talking of. Okay, in a Linux also you basically have the real-time scheduling kind of thing. So here, what will happen is you will come here, you are going to come here, you will try to acquire the lock. So now what is going to happen? You try to acquire the lock. The lock is not available. So what you will be doing? You will be doing a busy waiting. You will be spinning. Now, when you are doing spinning, You are a high priority thread and you are into the run queue. Okay, you are not into the wait queue, you are into the run queue. So that means you will keep on spinning. And I told you we are discussing about the scenario uniprocessor environment. That means there is only one processor. I can just execute one instruction at a time. So that means I can only run one thread at a time. So when I'm running this T2, T2 is in a busy wait, and as per the scheduler algorithm, as long as the high priority task is runnable, the low priority task will never get an opportunity to run. So I will keep on spinning, and the problem over here is I will keep on spinning forever because till I am in a run queue, till my high priority task in a run queue, low priority task is never going to get the opportunity. And since this no priority task will never get an opportunity to run, this unlock will never happen. So since the unlock will never happen, we are going to spin over here forever. So we have hit the scenario of deadlock where nobody can proceed. This T1 cannot proceed because it will not be given a processor. This guy cannot proceed because it is waiting for the lock to be unlocked. Now, lock can be unlocked only when this guy gets a processor. But since T2, which has a higher priority, is spinning, T1 will never get the opportunity to unlock the thing. So we are waiting for the event which will never happen. And this will result into a deadlock. Hope everybody is clear with this scenario. So now this is what the scenario is. Spinlock can result into the deadlock. So how do you basically overcome that? So on the uniprocessor environment, it's very easy to create the deadlock if Spinlock would have operated like this. But what we typically do is on the uniprocessor environment, whenever you take the lock, let's say this task T1 took the lock. As soon as it takes the lock, we disable the preemption. We disable the preemption. When we disable the preemption, that means the scheduling decision is not going to take place. That means even if T2 becomes runnable, T2 will not get an opportunity to run. That means scheduling decisions are on pause. No preemption. You are saying I should not be preempted. As soon as I take the lock, the on this particular processor, the scheduling decisions are on pause. That means even if P2 becomes runnable somehow due to some event becoming true or something like this, it will not get an opportunity to run. So that means if you have reached here, that means you will complete this without being preempted in between. Then the deadlock will not happen. But only thing you need to understand over here is the scenario called busy waiting will never happen on the uniprocessor environment. On the multiprocessor environment, of course, this can happen that T2 is running on the processor P1, PR1, and T2 is spinning on the processor PR2. That's possible. But when you have only single processor over here, as soon as you acquire the spin lock, the preemption is disabled and T2 will never get an opportunity to run. Okay, so you will complete the task to complete this thing to the finish line, and then only the T2 will get an opportunity to run. So that's how it happens in the uniprocessor environment. You disable the preemption on that processor. Does it make sense? So then it will never happen. Like while T1 is running, T2 will come and preempt it because scheduler is paused. Preemption disable means scheduler is on pause. Scheduler will not do the preemption. Scheduler will basically not take this process off. So if you have reached here, the spin lock is definitely available. If you have reached here, it's something which is always available. Otherwise, you wouldn't have reached here. Okay, you have reached here. That means it's available. Making sense?
Yes.
Okay, so now let's take another scenario. I have T1 and there is a resource which I'm protecting against ISR. Okay, there is a resource which I'm protecting against ISR. So a spin lock and spin unlock. And here I'm doing lock and unlock. And let's say I took the spin lock and the same fundamental applies. Like let's say T1 came and T1 acquired the spin lock. So preemption was disabled. Preemption disabled. Okay. Now interrupts, as you understand, are not dependent on this preemption. That means it's not the scheduler which schedules the interrupts. Interrupts are basically triggered by the hardware in response to the hardware. They don't come under the scheduler. So that means even if you turn off the preemption, still the scenario will come because interrupts are of high priority than the normal process context. So still you will come over here and it will busy wait and still it will result into a deadlock. So that means if you use the spin lock in a normal variant, the preemption is disabled, ISR doesn't care. Okay, because ISR is not being something depends on the scheduler decision. It's not the scheduler which schedules the ISR. ISR is triggered directly from the hardware. Okay, it will be coming from the interrupt framework. So again, you will hit the deadlock. Let's say you are in the middle of this and the interrupt got triggered. Interrupt comes here and it tries to acquire the lock. Lock is not available. It will do busy wait and you will run into deadlock. So what should we do in that scenario? Like when the resource is being shared between ISR, between the ISRs or between the ISR and the task. So here what you do is you use another variant of Spinlock where you disable the preemption as well as you are going to disable the interrupts. Disable interrupts on the local processor. So two things. So this variant we call it as a Spinlock underscore IRQ variant, which will disable the preemption, which will also disable the interrupts for us. Okay, so that means when you come here, even the interrupts are disabled, even the ISR cannot preempt you. Okay, so that's how the things work.